Hi everyone. So we are going to begin the final unit of the course this week, which is organic chemistry and instrumental analysis. I'm hoping we're going to be back in school for the instrumental section, but we're going to begin the organic section this week. Organic chemistry is predominantly carbon-based chemistry, and we're going to look at carbon and how it is involved in different types of bonding, the differences between single bonds and double bonds. And we're going to begin by looking at molecular orbitals, which takes the idea of carbon, its valency of 4, and expands on all that a little bit. So, before we get into this topic in great detail, I want to introduce to you a new way of drawing molecular structures. Now, you will probably have seen this before, but this is the way I would like you to draw molecular structures from now on. If we have a look at the two molecules I've got on the screen here, the first one is methane. It is one of the most simple molecules, organic molecules that we have. It's simply 5 atoms, 1 carbon and 4 hydrogens. It's quite small. It doesn't take a long time to draw. It's kind of difficult to simplify that structure anymore. But if we have a look at this second molecule, it's a good bit bigger. It contains a lot more atoms and would take up a lot more space to draw, especially if we were going to draw out all the little individual bonds to the hydrogens. This just for information, if you can't remember how to name molecules, you better have a wee look over that. But it's 2,2-dimethyl butane. So we're going to think of a way to simplify how we draw all these types of molecules. Right, so here is this structure again, just in the bottom right hand corner. Rather than drawing in all the individual carbons and hydrogens, I've essentially just left them out. And each end of a bond, or each angle in a bond or edge of a bond, would represent a carbon. Okay, so there's 1, 2, 3, 4 carbons, a methyl group there, and a methyl group here. Now, it would be up to you to work out how many hydrogens each of these little angles would represent based on how many bonds is that carbon forming. We know it forms 4 bonds in these alkanes. So that carbon in the middle there has a bond going up here, a bond coming here, a bond coming here, a bond going there. So it wouldn't be directly bonded to any hydrogens. This one is bonded to this carbon and this carbon, so there would be 2 hydrogens bonded there, and then all your kind of ends, your terminus carbons, all have 3 hydrogens each. Okay, so have a look at that structure at the top. It is very similar to the one on the previous page, except I've got a double bond in here between the second carbon and the third carbon. Why don't you pause the video here and have a wee think about what this would be called. So if we've managed to work that out, it would be 2,2-dimethyl butene. Remember, we always have to number in the name where the double bond is and where each of the methyl groups are. So I've got 7 examples here that I would like you to draw the skeletal diagram for. If I talk through a couple with you first of all, and then get you just to try the rest on your own. So if we look at this first one, nice and basic, I've got 1, 2, 3, 4 carbon atoms. So that would simply be 1, 2, 3, 4. That's my skeletal diagram for butane. What one am I going to show you now? I think I will show you this one here, this methanoic acid. I've got my carbon with a double bond up to oxygen. I have to draw in the symbol for the atoms that are not carbon and hydrogen. And then I have a bond coming down here to my hydroxide group. If that hydrogen was directly bonded to a carbon as part of an alkane chain, I wouldn't need to draw it in, but because it's bonded to the oxygen here as part of the hydroxide group, I would need to draw it in. Why don't you pause the video here and have a go at drawing that for the rest of them. So I've just added in there what the skeletal diagrams would be for the rest of those examples. If you just want to check, remember if there's anything you're not sure with, send me a wee email and we will have a wee look at it. Okay, if you're quite happy with skeletal diagrams, we're going to start looking at molecular orbitals. We're going to begin by thinking back to August when we looked at atomic orbitals. We thought about the shape of s orbitals, p orbitals and d orbitals. Now we're going to concentrate today on s and p orbitals and how they're involved in forming bonds. We're going to look at something called sigma bonds and pi bonds and how they are formed through something called hybridization. And then we're going to think about the bonding continuum. So if you think back to higher, and you would look at this in terms of the difference in electron negativities between the two atoms that are involved in a bond, and how the greater the difference, the more polar or almost ionic the bond would be. So I want you to think back to National 5, and you're asked how many bonds does a carbon atom form? You'd look at your periodic table, it's in group 4, valency 4, it forms 4 bonds. But let's think about what we have learned in advanced higher. Carbon has 6 electrons. Those electrons would fill 1s2, 2s2, 2p2. And your orbital box notation would look a little bit like that. Now, we would say that carbon has a valency of 4 because it has 4 unpaired electrons. But according to what we know about how orbitals are actually filled, that doesn't make sense because according to this, carbon only has 2 unpaired electrons. So there's something not quite adding up. And this idea of molecular orbitals, molecular orbital theory, will provide an explanation for more complex molecules, even though I said earlier it was simple, it's more complex than like a hydrogen molecule. Why does carbon in these types of molecules, like methane, form 4 bonds? Right, so we spoke about how atomic orbitals are the volume of space that electrons are likely to be found in. We know we cannot exactly pinpoint where an electron will be because they're always moving, but an atomic orbital is this space where an electron is likely to be found. So nice simple molecule to begin with. We have hydrogen. We know that in each of these hydrogen atoms, there is 1 electron in the 1s orbital. When we know that hydrogen naturally exists as H2, so these 2 orbitals, well, something must happen to them. They must combine in some sort of way. When orbitals like this approach each other, they begin to overlap and they form a bonding molecular orbital. A bonding molecular orbital can hold a max of this one here anyway, formed by the combining of 2s orbitals can hold a maximum of 2 electrons and would have a shape a bit like that. Let's continue to look at that combining of two 1s orbitals. And I want you to look at this statement that's written at the top. The number of molecular orbitals formed is equal to the number of atomic orbitals that combine. Now, we're combining two atomic orbitals to make one bonding molecular orbital. Quantum mechanics dictate that there must be an opposite effect of that combining of the atomic orbitals. So the two nuclei of the bond and the bonding electrons are found within this bonding molecular orbital, but at the same time there is an equal and opposite reaction to that, which is the formation of these anti-bonding orbitals. So this here represents the bonding between two orbitals. This would represent the dissociation. Okay, it sits at a much higher energy, as you'll see in the next slide. So is harder to do in a sense, which is why we always see the bonding. There is actually a third molecular orbital called a non-bonding orbital, and that is just where all the other electrons of the atoms would sit, the ones that are not involved in any bonding. So here's just a little look at those orbitals in terms of their energy. So say here we have 1s, 1s. As they combine, this bonding molecular orbital, as you see, it's notified there by a little sigma, and we'll talk more about that in a wee bit. Sits down here at a lower energy. Those electrons, those atoms, sit much happier when they're bonded together, so the overall energy comes down. But that equal and opposite effect of the anti-bonding, denoted by a little sigma star, that wee star just means anti-bonding, sits at a much higher energy. This is what we observe, and the anti-bonding is just the opposite effect of that. Right, so thinking back to bonding continuum that you looked at higher, we know that the symmetry of a molecule will determine if it's polar. The difference in electron negativity will determine whether it is ionic, polar covalent, or pure or non-polar covalent. Let's look at pure covalent bonds. So an example here of fluorine. So both atoms in a fluorine molecule have an electron negativity of 4. Because the pull from the nucleus in each of these fluorine atoms, remember the outer unpaired electron in each of these fluorine atoms will be in a p orbital, which is why we're seeing that shape there. The pull on those bonding electrons, so there'll be one in here, one in there, is going to be the same. So when they combine, we're going to see a nice symmetrical bonding orbital. Okay. 4.0 pull from here, 4.0 pull from here. I should maybe have drawn that down here, but it doesn't matter, you can add it in if you want. We have an equal pull on that bonding pair of electrons where those p orbitals have combined, giving us that nice symmetrical shape. So let's look at this in terms of polar covalent bonds. We have hydrogen chloride here. So just switch to the pen. We've got an electron negativity of 2.2 for hydrogen and 3.0 for chlorine. Because the chlorine atom has the higher electron negativity, it is going to pull the bonding electrons, which we see here, closer towards it than the hydrogen, making the chlorine end of the molecule slightly negative and the hydrogen end of the molecule slightly positive. So let's look at that in terms of these bonding molecular orbitals. Here we have our 1s of the hydrogen with an electron negativity of 2.2 and the chlorine 3.0. As they combine here, which is why we see this greater lobe here, because we've got an s orbital and a p orbital, and also because the pull on the bonding electrons is much stronger from the chlorine, we see an asymmetrical molecular bonding orbital. So just a quick note on the ionic bonds. Here we have quite a difference in electron negativity values. You should be, pretty comfortable with the fact that sodium chloride is an ionic compound. Because we see almost complete electron transfer, the bonding orbitals here will be extremely asymmetrical, and that's what we would observe in all ionic compounds. So let's start looking at these sigma bonds. Sigma bonds arise when two atomic orbitals form end-on. By end-on, I mean horizontally, like this. If we were in class, I'd be doing a lot of hand waving and all sorts of stuff, but we're not. So you'll have to make do with my arrows. They are orbitals formed by end-on overlap along the axis of a covalent bond. So if we have a look here, I've got two examples to talk through here. This could be hydrogen, okay? We have one hydrogen atom with an electron in the 1s orbital and a second, and they overlap like that, end-on, to form this molecular orbital. The bond that forms between those two atoms, which is represented here by that molecular orbital, is a sigma bond. Another example here, a slightly bigger molecule, although still quite simple, a chlorine molecule. We have our p orbitals where the bonding electrons are found in chlorine atoms. They overlap end-on like this and form something that looks like this, a bonding orbital that looks like this. So again, this is a sigma bond between the two chlorine atoms. That is, if we draw that in there just to highlight to you exactly where that is, this is the sigma bond holding the two chlorine atoms together. So let's revisit this question about why, if carbon only has two unpaired electrons, as we see from the orbital box notation, does it form four bonds? And we're going to look at this in the context of alkanes. Okay, what actually happens in these types of molecules is that the 2s orbital and the 2p orbitals form new identical degenerate orbitals. Okay, so let's just have a wee look at that. Here we have our 2s2, which is filled with opposing spins, and we have our 2p2. These four orbitals combine to give us an sp3 hybrid orbital. It's degenerate. See how it sits a kind of middle in energy between where you would find the 2s and the 2p orbitals. We have one electron in each, called sp3 because it's made of 1s and 3p orbitals. They are hybrid orbitals, and this is where our four unpaired electrons for carbon come from. So in terms of the shape of our sp3 orbitals, we've got to look at the shape of the atomic orbitals that combine. So we have our s orbital, which we know is just a nice simple circular shape, and our p orbital, which is this dumbbell shape. And when they combine, they have this really asymmetrical shape here. Okay, so it's an sp3 orbital is asymmetrical. That's not how you spell asymmetrical, but you know what I mean. This little lobe of this the shape of this sp3 orbital is not terribly important, so you might see it sometimes just drawn like that as a single lobe. It's strongly directional, which means all the electrons are really over here, so that it allows for easy overlap when it's taking part in bonding. Right, so how are these sigma bonds formed in alkanes? So we have our carbon atom with our sp3 hybridized orbital here. I'll just redraw in that carbon, might be a bit clearer. And our hydrogen, which is just simply a 1s orbital. They overlap end on like this. So the overlap region is in there, but just draw a circle. This is where they overlap. You'll notice that this molecular orbital that is formed, the lobe here, is much larger than this lobe here, and that is because these two have combined to make a bigger molecular orbital. So it has a larger lobe. So methane has 4 sigma bonds. Here is our carbon atom with our 4 sp3 orbitals there. We have a hydrogen coming to one of our sp3 orbitals, end on, another one end on there, another one here, and another one there. I'm really trying to get this idea of end-on overlap into here, which is really difficult from behind a computer screen. However, this happens 4 times around the carbon atom in each of the sp3 hybridized orbitals. So methane contains 1, 2, 3, 4 sigma bonds. So let's look at ethane. Ethane has 7 sigma bonds. It has 1 sigma bond that is formed between an sp3 on this carbon and an sp3 on that second carbon, and then 1 there, there, and there, and then single bonds between this carbon and hydrogen over here as well. So a carbon to carbon single bond is a sigma bond. A carbon to hydrogen single bond is also a sigma bond. Right, so in terms of the arrangement of the atoms and the bond angles that exist within alkanes, where sigma bonds are present, the angles are all set at 109.5 degrees, just like you should know from the first unit are the bond angles between any tetrahedral shape. That is of course due to the repulsive effect of the sigma bonds. So there's obviously quite a big lobe here, okay, and then quite a big one there, pushing them away. And when all that balances out between here, here, and here, we get bond angles in between every sigma bond of 109.5. So just to summarise sigma bonds, they show sp3 hybridization, which is when we have a hybrid of 1 s orbital and 3 p orbitals from a carbon atom. They are found where bonds overlap horizontally. Remember, end on, okay? I'm really trying to stress how important it is that you remember that. They've got a bond angle of 109.5. and they are found between carbon-to-carbon single bonds and all carbon-to-hydrogen bonds, which of course are also single bonds. So here we have an ethane molecule and an ethene molecule. And we looked a minute ago at how ethane has 7 sigma bonds, one holding the 2 carbon atoms together, and then one from each of the carbon atoms to their 3 hydrogens. A sigma bond can rotate, and the molemodes show us that quite nicely. Now here we have ethene. Our carbon to hydrogen bonds can rotate quite nicely, sort of indicating that they might be a sigma bond, but if we look at the double bond in between the 2 carbon atoms, they don't rotate. That suggests to us that they might be something different. So the video on the previous slide just done a little comparison using the molemodes of a single bond between 2 carbon atoms and a double bond between 2 carbon atoms, and what differences we actually see. A single bond, or a sigma bond, shows much more rotation, and the double bond, well, we can't rotate that at all, suggesting that, well, there's maybe something a wee bit different happening here. Further evidence to that is if we look at the bond enthalpy values from the data booklet. So our bond enthalpy values are just the amount of energy it takes to break 1 mole of carbon-to-carbon single bonds. So for the sigma bond, it's 348. In the carbon-to-carbon double bond, if both these bonds were sigma bonds, we would expect that value to be exactly double this, so 696, but it's not. It's 612. So the second bond here is clearly not a sigma bond. It must be something different. So that something different is a pi bond, and pi bonds are found where we have multiple bonds holding 2 atoms together, so a double bond or a triple bond. Pi bonds are seen where we see sp2 hybridization. And sp2 hybridization is where we take one s orbital and it hybridizes with 2 p orbitals, okay, giving us 3 degenerate sp2 orbitals, so 1 s, 2 p, and then 1 full p orbital. So when we have a carbon in a double bond, one of these carbons, one carbon displays sp3, which is where the sigma bond comes from, and one displays sp2, which is where the pi bond comes from. Right, so let's go back to our example of ethene, okay? And let's look at this ethene molecule here and identify our sigma bonds. So we have 1 sigma bond between the 2 carbon atoms, and then 4 between the carbons and each of the hydrogen atoms. But we still have a carbon here with a p orbital that is unhybridized. And those unhybridized p orbitals lie perpendicular to the axis on which we find the sigma bonds. This produces a new molecular orbital. And if you imagine this as 3D, it's a hard one to draw because you need to imagine it 3D. See all this green space here? That is representing our pi bond, our unhybridized p orbital forming this pi bond. And it wraps itself all the way around, sort of encloses it in a cylinder almost. This sigma bond, it encloses that in the cylinder. These bonds are formed by sideways overlap, so not end-on overlap, which we see in a sigma bond. They are sideways, so they come one on top of the other, horizontally, like vertically, almost, not horizontally. So how are sigma bonds and pi bonds different? Well, the sideways overlap that is observed in a pi bond is much less effective, which means that the bond is much weaker. So if you have a look at the diagrams there, I have the queen of everything, Serena Williams, representing a strong sigma bond. And I try to think of someone who I wouldn't feel bad calling weak, whose name began with P for pie. I could only think of Peter Pettigrew from Harry Potter. I hope you're all a fan, or else you've no idea what I'm talking about, but we're just going to go with it. So the pi bond is weaker than the sigma bond. So that is why the carbon-to-carbon bond strength, the bond enthalpy, is less than twice that of the carbon-to-carbon single bond strength. And when, an addition reaction, we're going to look at them when we look at synthesis, is attacked, it is the pi bond that is attacked first because it is the weaker. But that will all make more sense in a few weeks' time when we look at synthesis. So a little note quickly on the effect that a pi bond has on the sigma bond that's also in that double bond with it. The carbon-to-carbon double bond means that we've got 4 electrons being shared in this whole area here, 2 in the sigma bond between the 2 carbons and 2 in the pi bond. Because we've got 4 electrons in this region, we've got a stronger electrostatic attraction. So in terms of the sigma bond that exists between the 2 carbons, it's actually shorter and stronger. It's stronger because it's shorter in the pi bond than it is in the double bond, even than it is in the single bond, just because of that extra electrostatic effect of the pi bonds and the extra electrons in there. So we know that sigma bonds, when in an alkane, for example, alkane displays bonds angles of 109.5. They all sit in a tetrahedral shape. Because that pi bond prevents any rotation and movement in the molecule, it pulls all the atoms that are in the molecule into the same plane. So if I had a model of the molecule, I'd be able to sit them all flat on the table in front of me. So pi bonds adopt a trigonal planar arrangement. Just to note as well, if I had a larger molecule, let's say I didn't have that hydrogen there and I had butene, for example, okay, which I'll just very quickly and messily draw out. If I had that, these atoms here, the alkane end, if you like, would sit in a tetrahedral arrangement, but the alkene end would sit planar. Okay, so just to finish looking at alkenes and pi bonds, let's go back to an example of ethene. And just like we've done for ethane, we're going to identify where all these bonds are. So in ethene, we have 1 sigma bond, that's maybe not the best colour, between the 2 carbons, and then 4 between carbon and hydrogen, giving us a total of 5 sigma bonds. And then this whole area here, this green area, representing our 1 pi bond. Right, just to finish then, a summary of pi bonds. They show sp2 hybridization, which is the combination of 1 s orbital and 2 p orbitals. Remember, in carbon, that leaves an unhybridized p orbital as well, that gives rise to the pi bond. They are found where bonds overlap sideways, so on top of each other. They are the second bond in a carbon-to-carbon double bond, and they are significantly weaker than sigma bonds. That's all I'm going to throw at you this week. I think that's probably enough. I'm still trying to work out the best way to do this. I don't know if you like that 1 video per slide or whatever. If you didn't, I can try and do it all in one. but I thought that was maybe alright because it would allow you just to work through the notes. And anyway, you can let me know what you think. But yeah, send me an email, any questions, as usual.